Awesome. Okay, hello everyone. Thank you guys for being here. I'm here to introduce Theodora, who is an associate professor in the Computer Science and Institute of Cognitive Science at the University of Colorado Boulder. Her research focuses on effective computing, human-centered and responsible machine learning, and health analytics. And I'll pass it over to you now, Theodora, and you can add anything that you would like.
Thank you so much, Sarah, and hi everyone. It's really great to be here with you today. I'm not sure how many people are also new to CU Boulder, but I'm also new to the university. I'm new to the area, so it's really nice to kind of be here. Let me start sharing my screen. Can you see that? Okay, perfect. So great. So today I was thinking that we can start. We can discuss a little bit of my research on human-centered and AI and machine learning. I'm going to provide a brief overview of what we're doing in the Human Behavioral Signals Lab, and then in addition to that, I'm going to kind of zoom in a little bit in one type of work that we are doing. Which is mostly related to the analysis of microbehaviors in diverse team interactions, and mostly in analysis that relies on speech and language. So essentially, a little bit from my research path and my overall research from as a student and after that. So I started. So my research is mostly focused on human-centered machine intelligence. So this means that we are trying essentially to quantify human behaviors from all the signals and all the information that we can get from humans. And this can be either speech, which includes vocal behaviors as well as the language content. It can be facial expressions, body gestures, as well as all the signals that we get from people via wearable devices or via sensors. This can be heart rate, sweat activity, and so forth and so on. So essentially, I started my research many years ago as an undergraduate student, and at that point emotion recognition from speech was was kind of this new big thing. So at that point my thesis was focusing on that. Then at my PhD, more wearable devices were at that point hot. So what I tried to do there was to design knowledge-driven models for modeling the signals, the physiological signals that we get from wearable devices and how these associate with human behavior. After that, transitioning more into the academia, we have worked with my students on machine learning models and essentially robust machine learning models for quantifying behavioral outcomes. And in the recent years, because there are all these questions about AI and how AI can be responsibly integrated into our society, especially for these sensitive applications that have to do with humans, we have transitioned more into designing responsible and trustworthy AI models, and also how we can design AI models that can help decision makers and stakeholders make decisions. So overall, while we know that there are all these wonderful advances of AI, recently we had one more kind of AI revolution with generative AI. Still, there are all these questions, and these questions are more relevant now, even more than a few years ago, about how AI can be adopted and integrated in the society in an ethical and responsible manner. And this goes beyond just AI providing decisions. It also goes more into this human-AI interaction. AI now can assist people in their decisions. So there are all these open questions about how does human-AI collaboration look like? What are factors that affect human trust in AI? And how AI can be designed in a way that can augment human decision-making rather than replicating human decision-making. And overall, what we're trying to do as part of our lab is that we are trying to model complex and multifaceted human behavior through all the various cues that we can get from humans. And this can include visible cues, what we call overt cues, speech and language content, facial expressions, body gestures, as well as all the physiological cues that model the generative process that happen inside the human body. And we also acknowledge that human behavior doesn't happen in isolation. So there are all these contextual and environmental factors that affect human behavior, such as basically who a person is interacting with, what are the weather conditions, what are the overall conditions of the environment, and all these can actually be integrated into a holistic system that can detect effectively aspects of human behavior. And feel free to ask your, to kind of put your ideas and ask questions, or just provide your input over chat, or also feel free to unmute yourselves. So essentially what we're trying to do in our lab in order to address some of these challenges, first of all, we know that one important factor of trust in AI is the robustness, how well the AI system works. So as part of the thread that works on robust human-centered AI, what we're trying to do is that we are trying to design machine learning systems that can be robust across people, can be generalizable across different conditions, and that means that they can take into account context. They also take into account potentially human variability, which we know that is there, in order to make more reliable decisions, in order to provide more reliable outcomes. Beyond that, there is, since there are all these questions about the leaking of personally identifiable information, we are also working, first of all, on ways to estimate the risks that are related with these AI systems, estimate the risk of leaking of personally identifiable information if we build an AI system that detects human behavior, as well as mitigation strategies in order to mitigate those risks, to reduce those risks. Another very important research thread that has been actually in the past years, I think a lot of research communities are working on this, is about fairness. So we are trying to see what might be potential bias in the data and in the algorithms that might result in unfair decision-making. And what are the algorithms, and how can we design algorithms in order to address this bias? And finally, another research thread that is actually very near and dear to me is how can we design explainable AI systems with the constraint that these systems need to be used by humans. And depending on the domain, the explainability and the different factors of explainability might be different. So it might be different if we want a system to be used by a human user. That person, for example, might be a patient, and a different type of explainability that we might have to be worried about if an AI system needs to be used by a clinician for clinical decision making. So as part of this research thread, we are looking at designing explainable systems and finding explainable signal representations, but also we are examining the interaction between the human and the AI via a set of user studies. And these are some of the applications that we are working on. We are interested in mental health problems that have to do with mood disorders, adolescents risk-taking. We are also working on aging in place. So this is a collaboration that we have with landscape architecture and urban planning, as well as with construction science. And we're trying to see how the environment affects older adults' walkability, and how can we design interventions that are inspired by crowdsourcing biosensing data. And also another application is in the context of workforce training. So we're trying to see how we can design intelligent assistive interfaces that can support people in public speaking, or potentially during the interviews, or some type of intelligent assistive interfaces that can support teaming, especially in the context of diverse teams. So today, what I'm going to discuss is mostly our work on the latter, but I'm happy to discuss any other things offline as well. So going more into diverse teaming, we know that diverse teaming creates opportunities for approaching problems from different perspectives and inspiring innovative ideas. But of course, with that, there are a few challenges that might come into play. People who come from different backgrounds and different threads of life might have different experiences. And when they are all in a team trying to solve problems, they have to, at some point, converge to a solution, or potentially they have to provide divergent opinions in a matter that is productive for the team. On that front, we are working on two different projects. First of all, we are working on a project that looks into diverse teams in space missions. Space missions have this very unique characteristic in that they are of course, they have a very high risk. Because we're talking about unknown environments with little communication with the Earth. And in addition to that, they are quite longitudinal. Space missions can range from a couple of weeks all the way into months if we are talking about far space exploration. So we're trying to see how teams interact with each other during these types of missions, and especially what might be factors that might be affecting team outcomes. And the second application that we are working on in this domain is essentially our diverse teams in student teams at the university when we are conducting problem-solving exercises, and we want to see how these diverse teams would approach the problem-solving situation, especially if we have people with more or less experience with the task at hand. So I'm going to start with with the first research thread on teaming in space missions. And again, feel free to put your ideas or questions in the chat. So space exploration, as we discussed, demands an adequate team coordination and cooperation, since we're talking about environments that are quite unknown and sometimes hostile. And of course, also NASA and other space agencies acknowledge that there is an increasingly diverse astronaut population, and acknowledge the value that we get from this increasingly diverse body. And we are not talking only about sociodemographic diversity, but also we're talking about diversity of backgrounds. There might be missions where we have people from military background versus people who are from a less military background and are part of the mission more for scientific purposes. And the current efforts to quantify team functioning mostly rely on self-reports, which, while they can be to some extent reliable, they also can have subjectivity, can be inherent to subjectivity and recall bias. So the hope there is that signal-based measurements of the team interaction can help quantify aspects of the mission that might be interesting and might affect team functioning the most, in a way that they can objectively quantify team performance at high temporal resolution. Again, these signal-based measurements do not only need to happen only at the end, but they can happen pretty much continuously throughout the mission. Therefore, we can get more fine-grained temporal estimates of team functioning throughout the mission. And the second thread is on interpersonal interactions in STEM. While there has been a lot of work, especially in the affective computing community, on interpersonal interactions, there has been not so much research that has focused on the interpersonal interactions that are reflective of the perseverance of minoritized students in STEM. Also, there has been a lot of research on what are factors that affect minoritized students' experiences in STEM, such as student attributes, the curriculum, institutional practices. Still, there is not so much research on these moment-to-moment daily factors that might affect perseverance and types of behaviors that might communicate denigration, discrimination, or exclusion. So we're very much interested in these exchanges that might be subtle, but still they might affect the student experience, sometimes in a detrimental manner. So since we talked about subtlety, the types of behaviors that especially we're interested in this research thread are micro behaviors. And the term micro behaviors, especially microaggressions, has been coined by a prior work by Su et al. Some years ago. And micro behaviors refer to subtle linguistic and paralinguistic indicators of thinking and feeling toward another member, in our case of a team. And we are defining negative micro behaviors as micro behaviors that might be exclusionary, they create barrier to belongingness in the team, and they put down the target status. On the other hand, we define positive micro behaviors as these subtle behaviors that uplift the target behavior and promote inclusiveness, belongingness, and affirmation of one's competence. So we wanted to understand how these subtle behaviors, either negative or positive, first of all, how can we design machine learning systems based on speech that can detect those micro behaviors? And second of all, how these types of micro behaviors can affect team performance and team functioning. These are some examples of negative and positive micro behaviors within the context of a team. So examples of negative micro behaviors can be the refusal of joint activity, especially the continuous refusal of joint activity, one's ideas or opinions being minimized or ignored, minute-by-minute disagreements, or acidic humor. That's something that has high relevance for both our contexts. So, for example, in the context of our applications for space tasks, we have seen, for example, sarcastic or caustic comments towards groups towards other groups. And also another example is language that includes the name of a subgroup. For example, in our space application, the name reservist refers to a person who hasn't really served in the military, who hasn't really actively served in the military. So there are all these subtleties that can affect, to some extent, team performance. On the other side, examples of positive micro behaviors include information sharing, acknowledging one's success, recognizing one's experiences. These are all these inclusive, affirming behaviors that might help one feel more welcome to a team. And there is some work on micro behavior detection. Mostly there is a lot of work on NLP, on the language-based detection of salient negative micro behaviors, such as toxic comments and hate speech that usually relies on social media. And written text, and the way many researchers have approached this is to quantify linguistic cues via handcrafted lexicons and pre-trained word embeddings. Our application is slightly different because we do not really rely on written text, but we rely on these interactions, these spoken interactions between team members, which might be less structured compared to written text. And in addition to that, include a rich content of vocal information. That means that in addition to linguistic information, we also have the acoustics that might be important for the scenario that we're looking at. And also prediction of team functioning. There has been some work in the domain about that. There has been a lot of work in prior research about that. However, the prediction of team functioning has been conducted in terms of multimodal data. There hasn't been a lot of work who has seen how micro behaviors themselves can affect team functioning. So there is a little bit of a research gap there as well. So let's go to here to our first study, and that's a study that was conducted by my PhD student, Saiki Paromta. Saiki, with the collaboration from the Behavioral Health and Performance Lab from NASA, has gotten data from two NASA campaigns, NASA HERA campaigns, and HERA is a research analog that simulates environments in space. You can see here an example of this research analog. So astronaut teams go there for approximately 45 days in a simulated space mission as if they were in space. So the data that we had there were from 9 teams, and each team had 4 team members. And the data, audiovisual data, were recorded by lapel microphones and surveillance cameras. In our while data were recorded at a continuous level, we actually focused on a key activity that include the team interaction battery task, since that was a little bit of a more structured and constrained activity that allowed us to design this initial preliminary proof of concept that we can actually design machine learning systems that can detect micro behaviors from conversational data. So after that, after we got the data, there was this long process about, first of all, cleaning the data as well as annotating the data with the domain experts. The data was annotated based on examples that were provided before. So these were the lines along this data was annotated, and I'm happy to discuss more about this. And also at this point, we are re-annotating the data in a more fine-grained level that can detect more types of micro behaviors. We had multiple people annotate the data as well, and inter-annotator agreement was around 0.6. So some types of features that were actually extracted from this data were dictionary-based, lexicon-based features, and for that we used the commonly used Look toolbox in order to extract linguistic features that are quite interpretable, and they can indicate the linguistic and psychological and cognitive processes that occur throughout the conversation. In addition to that, we had another lexicon that was called StressNet. So what StressNet was a very equivalent lexicon to Look, but it was very much adopted to conversations related to space exploration. And I think that was also developed by NASA some years ago. In addition to that, we also wanted to take advantage of work in large language models. So we used a 300-dimensional parogram embedding that was trained on the paraphrase dataset, and we used this because it was supposed to be able to take into account semantics in an effective way, and semantics can be quite useful when we're trying to model these subtle behaviors. Now, in addition to that, we also extracted some acoustic features, and acoustic features can be indicative of speech intonation and prosody. These were a total of 384 features and include all the prosodic and spectral features that are the usual suspects in these types of applications. So this can be the energy, the zero crossing rate, which is indicative of speaking rate, voicing probability, fundamental frequency, and the null frequency captural coefficients here are indicative of the speech spectrum and the energy throughout the speech spectrum. Some of these are also indicative, some of these measures are also indicative of sarcasm or humor, which also are related to micro behaviors, the way micro behaviors were defined. And finally, we extracted turn similarity features. Since we're looking at interactions and we are looking at individuals basically talking to each other and collaborating with each other, turn similarity features have been stipulated from prior work that are quite informative of these interactions. So essentially, we're measuring similarity between speakers, and these similarity measures were based across these 3 dimensions. So we computed a cosine similarity between speakers in terms of lexicon-based features, language-embedding features, and acoustic features. And here are some initial insights that we got from some statistical analysis that we first did. So first of all, what we saw here was that passive voice, that negative micro behaviors had an increased use of passive voice. passive voice, we know from prior work that passive voice is related to indirect language, and we know that micro behaviors can be subtle, quite indirect. So it actually makes sense that passive voice might be increasing in micro behaviors. We expected that angry language content would be increased during negative micro behaviors, but we didn't see that. And that might be another indication where, because negative micro behaviors are quite subtle and the capturing angry language might be more prevalent in a speech, and the lexicons that were used to capture angry language might not be able to capture the subtle behaviors. That's why we do not see any change in angry language when we study negative micro behaviors. But interestingly, we saw that negative micro behaviors have an increased fundamental frequency. An increased F0 is an acoustic measure, and prior work has stipulated that increases in F0 can be indicative of humor and sarcasm. So that might actually make sense. And something that was also interesting was that in terms of acoustic and linguistic similarity between interlocutors, negative microbehaviors depict a decreased similarity, and positive microbehaviors depict an increased similarity. And that is also kind of consistent with prior work that is related to congruent versus incongruent behaviors. Usually, if we have a team and we have congruent expressions between team members, this might be indicative of positive behaviors, while the opposite might be indicative of negative behaviors, which is something that also our data reflects here. So after that, we wanted to see, since we have these features that might be indicative to some extent of the presence of the negative or the positive microbehavior, we wanted to see if we can build machine learning models that can detect the presence of a negative or a positive microbehavior, or none of the two, from these acoustic and linguistic features. We pose this as a three-way classification. So our three classes were positive microbehavior, negative microbehavior, and control condition, in which we had the absence of any of the other two microbehaviors. So we explored several systems here. In the first system, we just had an LSTM that included linguistic features from the sender team member, and by sender team member, we mean the team member that actually expressed the microbehavior. Since we're talking about an interaction, and since we understand, because this is an interaction, that the response to microbehavior might be encoded in the target team members' linguistic and acoustic descriptors, the second baseline system that we used there included turns not only from the sender team member, but also from the target team member. So essentially, these were two LSTMs. The first LSTM had as an input the features from the sender. The second LSTM had as an input the features from the target, and these were trained and fused at the end for a decision, for a final decision. And finally, we also used prior work. We also leveraged information from prior work that models the dialogue process between interacting partners. This is some work that has been done, especially in the NLP, for modeling conversations between humans and conversational agents. And then we adapted that for the purpose of our application. So essentially, what we did there is that we had these LSTMs that modeled linguistic representations from the target team member and from the interacting team members. But in addition to that, because there's all this work about how context is important, how the context of the conversation is important, systems 3 and 4 had information about the context of the discussion. So context was encoded in two ways. First of all, we had the task context, what specific task was the team doing at that point, as well as the dialogue context. And the dialogue information was related to regulating the conversation, asking a question or answering a question. And since there is all this work in dialogue systems modeling about how context can reflect and can be informative of the conversation, we adapted this work here in their own human-to-human interactions. So essentially, the linguistic descriptors of the target team member and the interacting team members interact with context information as part of these operations that are happening here. And then from each of these points of the system, we get a probability of the presence or the absence of a certain microbehavior. And all these probabilities are fused at the end in order to give us a final likelihood of microbehavior based on the task-specific embeddings and the dialogue information as well. And here are some of the results that we got. First of all, these are the F1 scores for the tertiary classification that was conducted based on the interpretable features. And these were the lexicon-based features, acoustic features, and term similarity features. And for this, we just used random forest as a very simple classifier there. So we see, first of all, that lexicon-based features that modeled psycholinguistic processes based on Luke were the ones that gave pretty much the best results. And we also saw that if we use features that were extracted from both the target and the center participants, most of the times these features perform the best. Compared to just using features extracted from the center participants. And that also indicates that there is some valuable information in the target, in the target that actually is indicative of the presence of the microbehavior. We also saw that term similarity features on their own are quite effective, given also the fact that term similarity features are very small in number. So that's something that actually is might be reflective of interesting results. We saw, in addition to that, that acoustic features were to some extent reflective, but when acoustic features interact with language features, we do not gain any benefits from that combination. Now, when we go to the neural network systems, systems 1 and systems 2 were the one in which we had an LSTM with the sender features, and then an LSTM with both the sender and the target features. And overall, we see that these two systems performed a little bit, the F1 score was to some extent smaller compared to the context-based systems, especially the context-based system in which we added task information and sentiment information as well. So that we thought was quite interesting, and that reflects the importance of incorporating context, especially in these applications that we are trying to model subtle behaviors. So we can incorporate context that might be indicative of what's going on in the conversation, what task the team is doing, what is the underlying sentiment of the team. But we can also incorporate information from both the sender and the target that actually improves the performance of the system. So how can we further leverage what we have here in order to say something interesting about team functioning? As a second part of this study, what we're trying to do is that we are trying to investigate the effect of microbehaviors to team performance. One way to do that is to investigate how interaction dynamics between teams can be indicative of the team functioning. And conceptually, that makes sense, right? If people have negative interaction dynamics, that at some point in the long term should be reflected on their performance, on their overall performance. So what we did there is that we tried to see to what extent instances of positive and negative microbehaviors affect team performance. For this, we ran a linear mixed effects model, and the reason why we did that is that we had multiple measurements per team. So the linear mixed effects model would take into account these multiple measurements. And essentially, what we wanted to see is how positive and negative microbehaviors and linguistic and acoustic markers that are present during these positive and negative microbehaviors, how this would be associated with team performance. So we found some quite interesting things there. We found, first of all, that positive emotion during positive microbehaviors, and here is the equation of the LME model for that. So positive emotion during positive microbehaviors is positively associated with team performance, which is something that we would expect. The more positive the interactions, the more a team is likely to have a convergence. The team members are likely to be convergent with each other and to have a nice momentum, and therefore most likely we would have some positive effects in performance. On the other side, the more the negative emotion is during negative micro behaviors, the more the performance drops, which is something that we would also expect. In addition to that, we also tried to see some additional linguistic markers that are indicative of the context and the nature of the conversation within the teams. So we in terms of that, we saw things such as to what extent team members express discrepancy, certainty, or differentiation. And what we found here was while differentiation was not statistically associated with performance, discrepancy and certainty were. So essentially, the more discrepancy team members expressed, the more degradation we had in performance, and the more certainty team members expressed, the higher the team performance was. In addition to that, something that was quite interesting was were words, linguistic content that were associated with more everyday processes like food, body, and sex. For example, we saw that if conversational interactions had more content about food, then it was more likely that the performance of the team would be higher. And that makes sense, right? If we try to make friends with people, if we try to be positive with people, many times food is a common conversation that comes into play. On the contrary, conversations that were related to sex during negative micro behaviors were associated with the degradation in team performance. So that might make sense because that might reflect conversations that had acidic humor or comments that might be denigrating for a particular group, and that might not be received well from particular team members, and therefore that might be associated with some degradation in performance. And finally, something that we have consistently seen in our previous analysis as well, words associated with reward are also reflective of an increase in team performance, which also makes sense. Like the more we try to be supportive of people, the more we try to reward them, that might actually help in making a team more inclusive. We would expect the same thing with achievement and affiliation. However, we did not see significant effects there. So in addition to that, what we tried to do there is that we tried to design machine learning models that can predict degradations in team performance. So what we did is that we took the linguistic content over the conversation terms, and then we designed graph neural networks that modeled interactions between team members. So in our case, we had 4 team members. The graph neural network encoded the interactions between these 4 team members. A few preliminary results that resulted from this analysis was that the proposed graph neural networks were more effective into predicting degradation in team performance compared to no graph neural networks, that's baseline 2. So essentially just using an LSTM, compared to no graph neural networks, which is baseline 1. So just using an LSTM to model the temporal information in the conversation. And in addition to that, we saw another baseline in which we still modeled the interactions within the discussion, but we did not use an LSTM to model the linguistic parts. We just used the feed-forward neural network to model the linguistic evolution within the sentence. And that actually makes sense, that not modeling the linguistic evolution of the evolution of the language descriptors wouldn't really provide too much information there. Okay. So in order to summarize our findings here, first of all, what we saw was that to some extent, linguistic and acoustic features can be indicative of negative or positive microbehaviors. We also saw from our statistical analysis that the subtlety of negative microbehaviors is reflected in the types of features that yield these statistically significant results, such as the presence of passive voice, the similarity between interlocutors, or the fundamental frequency. In addition, we also saw that incorporating context is important, and also incorporating features from both the sender and the target is important for detecting microbehaviors. Finally, we also saw that the linguistic markers that occur within those microbehaviors are indicative of the overall outcome of the team interaction. Specifically, we looked at team performance, and we saw that some of these linguistic markers that occur during the microbehaviors can actually be indicative of team degradation, team performance degradation. Where are we going forward from that? In addition to modeling speech, one very important modality that has not been explored at all are the visual cues. Subtle facial expressions, subtle physiological reactivity measures can be also informative in order to model this in a more holistic manner. And in addition to that, we have modeled this data only for a very specific task, the team interaction battery task. It would be quite informative to explore this data in a longitudinal manner over the entire set of 45 days and over the various tasks that teams are doing throughout these 45 days. And of course, this would require a lot of pre-processing and a lot of cleaning of the data to be able to do that. I'm not sure if there are any questions here, because that's the first part. And if not, I can go to the second part. Okay. So as part of this second part, what we tried to see is that we tried to see to what extent some of these findings can be further extended to diverse teaming in STEM. So we designed a study in which we envisioned that, first of all, we would like to collect expressions and experiences of microbehaviors from STEM interactions. We would like to also design acoustic and linguistic markers that can capture these microbehaviors. And in addition to that, we would like to see to what extent these microbehaviors can be detrimental for team functioning and eventually for how included or non-included minoritized students feel in STEM teams. Here, I'm going to just present some very preliminary analysis since we have only collected very few preliminary data, and now this semester we are in the process of collecting more data. So far we have collected data from 2 teams of 3 students, and then we try to have this unbalanced. We are looking specifically at minoritized, gender as a specific factor, and there are also so many other factors that we can look here, such as race, ethnicity, and whether one is a first-generation student, but we started with gender in this specific proof of concept. So we had 2 teams of 3 students, 1 male and 2 female, and then 1 team of 4 students, 2 male and 2 female. The reason why we did that is that we wanted to see in these cases whether the other female student would act as an ally or as a bystander. This was the racial composition of our team. And their years in the undergraduate program. Students were recruited through mailing lists, and they were given pseudonyms in order to protect their confidentiality during the interaction. We tried to have these interactions online since we actually acknowledge that a lot of conversations and a lot of collaborations now are happening online. So it would be interesting to also try to see to what extent these expressions can occur in online interactions and how prevalent this might be in online interactions. And this is the study protocol that we had here. So essentially, our teams met over the span of 5 days. They completed some individual difference questionnaires, such as personality, coping resilience, stressful life events, and locus of control before the start of the study. And then throughout these 5 days, they conducted 10 problem-solving activities, 2 problem-solving activities per day as a team. Now, after each problem-solving activity, each person within a team separately had to complete a self-report of positive and negative affect, perceived stress, as well as perceived team functioning. At the end, people also completed a self-report on perceived micro-behaviors, negative and positive micro-behaviors, and they also had a debriefing in which they were told what this study was about. We had obtained IRB permissions for this study, for all the parts of this study. So a few very preliminary results here. These were from our undergraduate student, Chiara Berry, who had conducted some of this analysis. So essentially, we saw some interesting findings in that self-reported stress was associated with non-fluencies, with analytical thinking, with reference to friends, and mail references. In addition to that, positive affect was associated with achievement, references of achievement, and references to present focus, which is quite interesting there, since we would expect, again, this achievement, this language related to achievement, to have a spillover on positive affect. Second person pronouns were associated with team viability. And this is something that we know also from literature on couples, right? We know that, for example, if we use second person pronouns, we might be more inclusive, and we might actually give other people the chance to talk and express their opinions. And finally, language related to emotional tone and swearing was positively and negatively, respectively, associated with conflict management, which is something that we would expect. What we're trying to do moving forward, again, this was data only from 3 teams. We are expanding our data collection to more teams this semester, where we have definitely to conduct this analysis to include more teams and see how these results will pan out. We are also trying to see how we can code these interactions, how we can annotate these interactions in terms of the occurrence of positive and negative microbehaviors. And we have really this sample of positive and negative microbehaviors of coding from the space mission, but this needs to be adapted to these STEM-related interactions, and specifically also to these online interactions, since the nature of some of these online interactions might be different. We would like to not only to design machine learning models that can detect microbehaviors, but we would like to get insights from the analysis that can let us understand to what extent, what is the linguistic content of microbehaviors, what are the situations in which microbehaviors are expressed, what is the reaction of the target people to microbehaviors, and hopefully, with the collaboration of people, of researchers in communication sciences and social sciences, we would like to see how can we leverage these insights in order to design educational content, training interfaces, potentially personalized intervention strategies that can help mitigate negative outcomes from some of these negative microbehaviors, and of course promote positive microbehaviors. As you can all understand, there are a lot of there are all these technical challenges that are present in this research, but of course there are also all these ethical considerations. For example, even if we have a machine learning system that can detect microbehaviors, let's say at an 80% rate, is this enough? Should we have a 95% or 99%? How can we handle false alarms? How can we inform people, and should we actually inform people about negative microbehaviors? How can we do this? What is the most constructive way to do this? How can we consider the intent of the sender? For example, have they received training about some of these interactions? So these are all open questions, and we are very much interested in pursuing some of these questions later on, after in tandem with establishing the technology for doing that. In addition to that, I want to say that we have some research opportunities in our lab. As you probably have seen, there's a lot of speech analysis and language analysis that we are doing. There are these kind of speech processing opportunities for health applications that focus on adolescents' risk-taking behaviors, and these interactions are in Hebrew. And in addition to that, we have some natural language processing opportunities for interview training. We have another corpus that we have collected with interviews, and we are very much interested about processing the linguistic content of that, and also potentially using generative AI methods to further suggest effective answers that can augment interview training. Other than that, I would like to thank people for taking the time to be here today. I'm happy to answer any questions. These are some of our pictures from the various conferences and presentations. Thank you, everyone.
Thank you so much, Theodora. That sounds really, really interesting. I'm excited that you've joined us this fall. Does anyone have any questions for Theodora before we end the call? It looks like we have one. You can unmute yourself.
Good afternoon, Dr. Theodora. Thank